Hi everyone, this is Mr. Kerr. In this video, we're going to be looking at properties of gases. So I thought I'd start with looking at what makes a gas, what makes the gases different. So I'm going to look at different states of matter, just a quick review. And you can see here we've got a solid state. And in this particular example, we have oxygen, doesn't really matter. But when you have a solid, you have relatively high intermolecular forces acting on the particles. And as a result, the particles can't really move very much. They can vibrate back and forth a little bit, but they cannot move more than that. Also, because there's such high intermolecular forces, there's very little space between the particles. And as a result, the particles cannot be compressed together anymore. And there's a very, very high density of in solids. So let's look at a liquid. So liquid, you see the particles are moving around a little bit more. And the whole reason is because the intermolecular forces are a little bit weaker between the entities. And what we can have here, the particles are vibrating back and forth, but they can also be doing some circles. They can flip around and spin around. So we have something called rotational movement. So the particles can move a lot more freely. They're still tightly packed because remember, you do have the intermolecular forces, but again, they're not as strong as they were before. Now let's look at a gas. So gases, very obvious, there's very, very little attraction between the particles. So because of that, the particles are moving around on their own. They're moving from one location to another. We call that translational motion. And there's a lot of space between the particles. So this accounts for a lot of the properties of gases. And if we were to open up the container, these particles would have so little attraction, the particles just kind of separate from the other particles around them. So obviously, gases are very, very, very different from other states of matter. So let's take a look at what we can do in terms of understanding them. So the first thing is just what we went through. This nice summary chart here, talking about the different types of properties of solids, liquids, and gases. You might want to pause and take a look at this. We also have this great summary here. And the big thing is recognize the differences between gases and the other states. So again, gas particles, there's very, very little intermolecular forces. There's a lot of space, so they're very compressible. There's a lot of motion, and the particles are relatively independent because of the lack of attraction between them. So one thing we have to do is we have to develop a model to help us understand what happens with gases. So we use something called the kinetic molecular theory of gases. And this is just a way that we can interpret something we can't see. Gas particles are tiny. We cannot see them. So we have to understand what's going on. And the way we do this, we develop a model. And that's what this KMT theory of gases is. So let's look at some of the ideas behind this theory. So we have to assume a couple things in order for this theory to work. So first thing we have to do is we need to understand what kinetic energy is. And kinetic energy is simply these particles zooming around here. It's the energy of motion. So the faster you're going, the more energy you would have as a result. And what happens is as you increase the temperature, the particles are moving faster and they have more EK. Very, very simple. And the particles can move in one of three ways. We've seen this before. The back and forth movement from one place to another is translational. The spinning is motions called rotational. And finally, the back and forth jiggliness is called vibrational motion. So now we know about that. Let's look at this kinetic molecular theory. So first thing, gas particles are really, really, really tiny. They're so small, in fact, if you think about it, if gas particles were the size of grains of sand, a small container, a syringe of gas, might be the size of the school. So very, 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 very tiny. The other thing is these particles, because they're so tiny, there are very few attractive forces acting between them, or even repulsive forces. There's no forces acting on them. So we make a big assumption there. Real life, there probably is. Depending on the gas, some gases have a lot of attraction. For example, water vapor. Some have very little attraction or repulsion. Gas particles, we assume, are also in constant motion in straight lines. And this is true for the most part, but remember, the gas particles do hit the sides of containers, they hit each other, so they change direction all the time. And the particles are not always moving exactly the same way. Some might be moving really quickly, some of them are moving a lot more slowly. So on average, particles are always in motion. The next thing is that collisions are something called elastic. So when a gas particle, here's one over here in red, it hits the side of the container, another particle, the energy is not lost. It's not like a goop of, like, I don't know, slime hitting the wall and it sticks to the wall and the energy's gone. No, what happens is it's like having two super balls, two rubber super balls. They hit each other, they bounce, and the energy is returned. So the collisions are elastic. And the final thing is as the temperature increases, so does the kinetic energy of these gas particles. So altogether, these postulates or ideas form this kinetic molecular theory of gases. Now, if a gas follows all of these ideas, it's said to be an ideal gas. So sometimes this is called the ideal gas law. The only thing is, no gases are ideal. All gases, the gas particles, have some attraction between them. We have these collisions where energy might be transferred to the walls of the container, so some of it's lost to the particles. So there are little inconsistencies, but overall, though, this is a very useful way of thinking of gases and helps us understand a lot of phenomenon. Oh, so I'm just going to skip this part. So what we can do is we can use this kinetic molecular theory of gases to explain things. So here's a great example. Why is it that I can take a plunger, a syringe, fill it with gas, some air or whatever it might be, and I can push down on the plunger, and why can't I compress the gas? What is it about gases that allows me to do so? So pause the video for a second, think about it. What is causing this? What allows this to occur in the kinetic molecular theory? Okay, now that you've thought about this, let's check it out. So the whole idea here is that gas particles have a lot of space between them. And this is due to the very low intermolecular forces. There's no attraction, so they're spaced out. And as a result, what happens is when we push down on the plunger, the particles can easily be compressed together. Now, the other thing that happens, there's another property, is pressure. Now, pressure is how the push on the walls of the container by all these particles. So each time a particle hits the walls of the container, there's a little bit of a push. And each individual particle doesn't have a lot of push, but if you add up the trillions upon trillions of particles, there's definitely a push on the walls of the container. We call that pressure. So here, when the particles are all spaced out, the pressure is very low. And the reason is we have all these collisions, but what happens is these collisions are spread out over a large area. So if I look at an area over here, there are very few particles hitting on the wall there. So the pressure is low. Now, if I take the same number of particles, if I compress them, in the same area, I have a lot more particles. And because I have a lot more particles, there's a lot more push on the walls of the container there. We have much higher pressure as a result. All right, let's look at the next one and try to explain the next one with the kinetic molecular theory. So what's going on here? Or even better, here. Why is it that when you put a balloon in a hot environment, why does it expand? And if it's a cool environment, why does the gas inside contract, reduce in size? So think about this as well. Use the kinetic molecular theory. We'll be back in a bit. All right, now that you've had a chance to think about this, let's look at what happened here. Well, as the gas is heated, each of the particles, remember, is picking up more and more energy, more kinetic energy. You double the temperature, you double the amount of kinetic energy. So these particles are zooming around. Now, when they're zooming around, remember, they're colliding with each other. They're also, importantly, hitting the walls of the container. And they're hitting the walls of the container with a lot more energy, a lot more force, push. And this means that there's more pressure acting on the sides of the container. So there's more of a push on this balloon. Some materials, if they're elastic, can change their shape. So what happens is the push is changing the size of the balloon. The balloon gets larger because the volume of the gas inside gets larger. So it's a neat phenomenon. So again, you should be able to explain what's going on here using the KMT. So talk about the kinetic energy increasing as temperature increases. Talk about the increased force acting on the walls of the rubber balloon here. and talk about the increase in volume because the container is elastic. So all of these phenomena can be explained with the kinetic molecular theory of gases. Now remember, no gas is ideal, just like no student is ideal. However, you guys come really close, and so do most gases. That's it. Much